Okay, we've got a What the Physics video. This one is about the acceleration equations, the big five. We're going to touch a little bit on acceleration due to gravity. So, we've been dealing with acceleration already for a while. We just have the basic idea of acceleration is delta v over delta t. We also have the idea that we can get acceleration from graphs, yes? But graphs can be a bit difficult. We have this. If we knew our delta v and we knew our delta t, then it's easy. But what if instead we had displacement? Or we were looking for displacement? What would we have to do? Well, we'd have to go all the way from a position time graph to a velocity time graph to an acceleration time graph. So we'd have to make several graphs. We have to take the slope and stuff, or vice versa. Starting from an acceleration time graph, we take the area under the curve, get a velocity time graph, take the area under the curve, and finally we'd be able to find displacement. And that's possible, but it's rather time consuming. It's going to be easier via equations. Okay. Apparently we have Conan O'Brien here with the... anyhow. So the big five equations. These equations can only be used when we're talking about constant acceleration. For the first part of this year, we will be focusing on constant acceleration. There will be several times during this course that we will not be dealing with constant acceleration. In some cases, that's because even though the magnitude of the acceleration is constant, the direction is changing. Acceleration is a vector. Okay. The other scenario is the magnitude itself is changing. That's the only one I can think of offhand with that is some type of oscillatory motion. Pendulum, actually, we talked about pendulums swinging back and forth. The acceleration is changing there, depending on how closely you look. Also, if we had a spring bouncing up and down, that is going to have a changing acceleration. But we'll deal with that later on. Also, when many of you move on to AP Physics C, and that course you'll have calculus in it, then you'll get the chance to do derivative, because that's a real word. You get to do more calculus stuff. Okay? Yeah! Okay, so here we are with the big five. And you say, what? What the heck is this?
And the little five?
And the little five. No, actually, these are bigger than the equations. But so the slightly amusing story. I say slightly. I think it's hilarious, but. So I haven't always just taught it at lovely Centerville High School. I've also taught elsewhere too, and a number of years ago, back in the summer of 2004 actually, I was lucky enough to go on an exciting expedition with other physics teachers. Like, oh, with other physics teachers, that was woohoo, right? Okay. I bet you derived equations, right? Okay. Actually, we went over to Africa, specifically Southern Africa, specifically South Africa and Zambia. And we worked with physics teachers out there, and we're helping them to develop their courses. And it was a whole lot of fun. I learned a lot in the process about physics and other stuff. And so I was lucky enough to do that over the next 2 summers as well. But anyhow, this first summer, back in 2004, it was my job to go there and talk about kinematics. So everything we've been talking about so far. So I said, great, I'll go ahead and explain how I do the big five equations. So I have my PowerPoint all set up and everything. And so we fly over there, and it's like, it's halfway around the world, so it's quite a long flight. We get to the airport, like, I'm scared and excited and everything. So there's like this gift shop right outside the gate, and it was like, oh, get a poster with the big five on them. I'm like, oh wow, that's kind of weird. Get a T-shirt with the big 5 on them. Get commemorative plates with the big 5 on them. Get shot glasses with the big 5 on them. I'm like, wow, they take their physics equations very seriously here. And I mentioned that to the physics teachers when I got there, and they're like, no, that's not it at all. The big 5 is the big 5 game animals of Africa. So
I'll tell you about the little 5 later.
Okay. We have the lion. This is the leopard. This is the only animal that we didn't see. All these other ones we had actually taken pictures of. Cape buffalo, of course, elephants, and a rhino, or specifically a white rhino. And as you can see, the rhino was on the road, and there's a car. This is not our car because we were on the other side. And this car was being a real jerk because he just kept coming forward, thus pushing the rhino right toward us. And, it's cool for pictures, but then you realize there's the rhino coming right toward you. And, we'll just back up, and it just kept coming toward us. We're like, okay, get off the road. And so we did, and the rhino kept coming toward us. And we're like, back up farther off the road. And then we realized a very, very bad mistake, because the Zambezi River was right behind us. And that has a lot of crocodiles, and it was just like, oh, rock and hard place right now. Luckily, the rhino went by and kind of snorted at us. I don't know, it was a what's up, or anyhow. That was a good time, right? So, after we talk about the big 5 animals of Africa, we talk about the actual physics equations. I was showing them, and there they are, right? Here they are. The next several slides are on their derivations. We're not going to spend any time on that because these are things that you can look at and see and just kind of look through. Okay, I think it's really cool how they're derived, but it's not like a requirement that you do these. I will say that I give the big 5 equations, and this is different from most other physics teachers. And actually, these equations are listed a little bit differently than in the standard AP physics equations. It's not to say that these are illegal or anything, but these will not be on the sacred equation sheet. In my opinion, I think AP Central got that aspect wrong, but they don't listen to me. The only ones that you'd see on there are this first one, VVAT, this third one, the 1/2 AT squared, and then this fourth one, the V final squared. Okay. They don't bother including this second one and this fifth one because they figure you can derive them if necessary, which I'm like, oh, because that's easy to do on a test. Or you could just solve multiple equations to get whatever you need, and I'm like, oh, because that's easy to do on a test. But whatever. Like I said, there are the derivations. I even try to give it like graphically. Like you can see if you take the area under the curve and you take the slope, and it works. And I tried to do it all color-coded so you can look through and say, oh, okay, I see how that combines with that. Oh, I just went really fast. Yeah, it's not color-coded on a black and white print-off. I understand that. Just because you're not imaginative enough to see the colors on a black and white paper. Don't blame me. You might see a slightly different shading. I don't know. But these you can find these on Blackboard too. Or you can just look through here and pause. And say, oh, there it is. Right? Okay. So these are the equations again. These are the variables again. Like I said before, official physics equation sheet is slightly different. Instead of using D for the displacement, they use delta X, which sometimes confuses people because then they think delta Y doesn't apply. It does. Okay. Anyhow, here's a list of the variables. Notice that there are 5 different equations, and there are how many different variables? 5 different variables. Right. Coincidence? Nah. Nah. Okay, each equation has 4 variables in it. Okay, so this one has v initial, v final, acceleration, and time. It does not have displacement. This one has initial, displacement, final, time. It does not have acceleration, and so on. So the thing is, you only need 3 pieces of information to solve for the 4th. There's a total possible 5 pieces of information you could have. In order to solve for any one of them, you would need 3 pieces already. And you could solve for the 4th, as well as the 5th if you wanted. Okay? But in any particular question, you'd somehow be given 3 pieces of information, and then you wouldn't care about one, and you'd have to solve for the last one. And that is what's super cool about this method. You know you're going to have to list out your variables and draw a diagram of what's going on, draw a graph, draw whatever, okay? But listing out your variables is super important in helping you figure out which equation to use. You say, okay, well, let's say I have initial velocity, I have final velocity, I have acceleration, and I'm looking for time. Okay? Or any 3, and you're looking for the 4th one, right? How are you going to solve this? Well, you say, well, I need something with initial velocity. And, well, it could be this one, could be this one, could be this one, could be this. Oh, it's not this one. I need something with final velocity in it. Well, it could be this one, could be this one. Oh, it's not this one, could be this one, and so on. Instead of doing all that, why don't I just look to see what I don't care about? And I'm going to choose the equation that way. It's a lot faster. It's like the same thing I do when I'm taking attendance. I don't have to go through and look at everyone here. I can just say, where are the empty spots? And do attendance that way, right? Okay, if I have, well, I'll just say it's the first one. If I have initial velocity, final velocity, acceleration, and I'm looking for time, I don't care about displacement. So I'm going to use the one that does not care about displacement. Boom, right there. What if I don't care about final velocity? Which one am I going to use? Yes, this third one, right? Okay. See how fast that is? What if I have, let's see, I'll do it a different way. I have initial velocity, final velocity, time, and I'm looking for displacement. What do I not care about? I don't care about acceleration. That's which equation? The second one. Yes. Okay. See? Nice and quick. All right. Okay, so problem-solving techniques. First of all, just like anyone, you're going to read the problem thoroughly, very carefully. Make sure you really realize what you're asking. Because I can sometimes cruise through problems too, and if I'm not being attentive, I'll answer it wrong. And I've had plenty of experience with this. I mean, not experience answering things wrong, but, well, maybe a little bit. Sketch out a picture, graph, diagram. Several different ways I'm sure you can think of to indicate you have a good concept of what's going on. List out your knowns and unknowns. Think about what you're trying to solve. Is it a nice straightforward thing? Do you need to do multiple equations, multiple concepts? Select your equation, solve for the variable, as in rearrange it in variable form. It's one of the things about the AP exam is they are going to have a lot of stuff just plain variables. So you have to practice rearranging variables. Substitute in the values and calculate, checking by estimation, units, and reasonability. Okay, checking by estimation. I know you guys like to use calculators for all your math, and you still can. You're still allowed to use calculators on the AP exam. Okay, but you shouldn't just be able to rely on them. You should be able to do some mental math in your head. Okay, if you don't know what 14 times 12 is, okay, but you could estimate it pretty reasonably, right? Anyone know what 14 times 12 is?
168. Yeah.
Okay. You guys would know that, wouldn't you? Okay.
I just did all thumbs up and then added.
Okay, sure. Okay. for checking purposes, you say, I think that's pretty good. I could check on my calculator. If I'm just checking for order of magnitude, I can say, well, yeah, 12 is practically 10, and 14 is practically 15. So 10 times 15 is 150. It's not the exact answer. I didn't expect it to be. It's pretty close, right? Estimation. Units, of course, we've been harping on those for a while. And reasonability. Does it make sense that you are now driving your car at 2,000 meters per second? No. Okay. We got some example problems. You can try these on your own as before. A baseball pitcher. I've even included some of my bad jokes. So drawing out the pitcher. The pitcher, the baseball. And then when I ask you to do the checking, I say like, okay, check if this is a reasonable one, like check for estimation. I'd say, is this a ballpark figure? Yes, I know. Too bad you're not a teaching genius. Okay. Another one for just a car. How does the car accelerate? Okay. So work through. Okay. Good stuff. Questions on that? Right. We'll do a few minutes on this. What do Galileo Galilei and Tom Petty have in common?
I have no idea who Tom Petty is.
Yes, indeed. Say it loud so we can hear it on the Free Fallin'. Yes. You don't know who Tom Petty. Okay. Yes, singing the song. Free Fallin'. Yeah, it's not Mr. Fair there. Okay. Yes, free falling. Anyhow. Yes, Tom Petty sings a song called Free Falling, and so Galileo also sang that song, right? No, but he was known for dropping things, right? Not because he's a klutz, but at least according to legend, he went up on the Leaning Tower of Pisa and dropped stuff.
Before it was leaning, right?
He did not cause it to lean, no. Yeah, and they kept trying to compensate for it, and yes, they made it kind of weird and kind of worse, but it works. Cross-cultural references, yay! All right, so I have a pen in my hand. If I take a look at this pen, you might see this as a very, very special pen, right?
Yeah.
Okay, it writes. Oh yes, I know, but beyond that, it's what's called a test mass. Everyone's, oh, I didn't realize. Okay. You had to send away specially for that, right? You're certified and stuff. Okay, a test mass is a mass that's relatively small to the Earth, which, I think pretty much anything around here is, other than the Earth. And I can let go of this, and I can watch it fall, and I can see it is moving downwards. Okay, and if I bring this to some other part on the Earth, I can do the same thing. And for the benefit of those people that can't actually see me dropping the pen, I'm dropping the pen. Okay, and if I keep doing that in different parts of the world, I'll be able to map out how this particular pen will fall. You say, great, I don't care about this particular pen, I'm talking about stuff in general. This is a test mass, and it will work just the same as any other pen. Okay, I had to pay $400 for this special test mass pen, but it's worth it, right? I'm teasing you about the $400 thing. It's still worth it. Anyhow, everything is falling at the same rate, and that's good stuff. That is because of Earth's gravitational field. Oh, be very careful about the word gravity. Gravity itself is a reference to a force, gravitational force. Gravitational field is not the same thing as gravitational force. Okay? So what I would really like you to do is distinguish what you're talking about. And this is very unfortunate because the acceleration due to gravity is often referenced as little g. You say, oh, gravity, right? Yeah. No. Gravity is a force. So if you could just distinguish gravitational force when you're talking about gravitational force. No, that was a stupid statement. Say gravitational force when you mean gravitational force. Yes. when you're talking about acceleration, that's little g, you can say the acceleration due to gravity, or you can talk about the gravitational field. As far as we're concerned, they're the same. It's kind of different, but it's fine for right now. The acceleration due to gravity on Earth, how fast this pen was falling, or how it's affected, that's accelerating at 9.8 meters per second squared downwards. If we're saying downwards is negative, then we'd put a negative sign in front of it. We don't have to say downwards is negative. It depends on whatever reference frame we'd like. Say, why would we not want it to be negative? I don't know. We're moving downwards. It's accelerating downwards. Why not use positive, right? It all just depends. You'd have to indicate what you're doing on the reference frame, but it's fine to use that. Anyhow, as this is falling, we've also got to talk about its initial velocity and its final velocity. One of them is 0, but chances are it's not the one that you're thinking of. So as something is falling, it's speeding up, right? Until it comes to a stop. True. But when I'm talking about something falling because of gravity, I'm talking, if I have this pen in my hand, as soon as I let go, as soon as I remove contact with the pen, that's the initial velocity. What is that going to be? 0. I didn't throw the pen downwards. I mean, I could, but in this case, I didn't throw the pen downwards. I didn't toss it upwards. I just released it. So the initial velocity is 0. It hits the table. So that means the final velocity is 0, right? As it's sitting on the table, is it accelerating due to gravity? No. It's just sitting there, right? And still sitting there, and still sitting there. So it's not even accelerating. So we cannot use the sitting here velocity as the final velocity. What we'd be talking about is what you can call the impact velocity. Just a split second right before impact.
It's like everything up to but not included.
Yes, up to but not including. If you remember what we were talking about with limits earlier, so just right before it hits. You have to say in a high-pitched voice to make sure it's clear. There you go. Okay? So it's as soon as you let go, it's right before it hits. Because you can argue, hey, what if you try to catch this in your hand and you bring your hand down with it as it's coming to a stop? Okay, well then we got something different, yeah? Okay, good stuff. Good stuff. We'll stop there. We'll learn about how you're under the influence. All the time. Yeah, no, you are under the influence right now.
Yeah.
Okay.
Many things.
We'll discuss that later. Physics.
Okay.